Let's look at this problem where the problem is to figure out the unbiased estimator for standard deviation. So to start with, the observations are all Gaussian with some mean mu and variance sigma squared. So you have x1, x2, etc., xn, n observations. Each xi is independent, identically distributed random variables with a common mean mu and variance sigma squared. So of course, mu is the expected value of any one of these xi's, and sigma squared is of course expected value of xi minus mu the whole squared. But generally the problem is both of these quantities are unknown. So IID of course stands for independent, and the second I is for identically distributed. Random variables. So they all have common mean mu and common variance sigma squared. So of course the joint density function, you look at the joint density function is the product of the density functions, and each of them are Gaussian. So if you form the likelihood function, you take the find out the maximum likelihood estimates for mu and sigma squared are generally easy. So without going into the details, the best maximum likelihood estimator for the mean is in fact the sum of all the observations. And you can see clearly this being a linear function, it's an unbiased estimator, and since all of them are independent, the variance is also sigma squared over n. In fact, this is the best estimator for the mean. So this is the minimum, this is the unbiased estimator with the minimum most variance, and hence it's the UMView or uniformly minimum variance unbiased estimator for mu. We can also do the, so similarly if you want the unbiased estimator for variance can be shown to be, so these are classic results, and it's also easy to show that if you want the sigma squared to be, remember x bar itself is, so this is your x bar, which is mu hat of ml. So this is the best estimator for the mean, average of the observations. Then from each observation you subtract the average, square it, add it up and divide by not n. Unlike here you divide by n minus 1. Then this can be shown to be an unbiased estimator. And so in fact expected value of sigma squared hat, this quantity ml, is in fact sigma squared. That's what we mean by an unbiased estimator. And it's a variance, and this is a chi-squared with the n minus 1 degrees of freedom. Consequently, it's a variance of this estimator is actually 2 over n minus 1 sigma 4. So these are classic results. This is also problem 8.20. So solve the problem chapter 8, example 20 in Papolis, 4th edition, Papolis Pillai. Of the probability book. So I'm not going to go over the details. And again, you can show that this is the minimum most, this is the best estimator for the variance. But the peculiarities in statistics is, suppose we are interested in sigma, the best estimate. Sigma is of course the standard deviation. That's what we mean by standard deviation. So let's say we are not interested in sigma, not interested in variance, but interested in standard deviation, an estimator for the sigma. So you may say, if you have an estimator for sigma squared, why not take the square root of this? Of course, you can take the square root and that is an estimator, but like here, we also want the estimator, so that's where the difficulty starts. We want this estimator to be unbiased. If you just take the square root of this, the expected value of the square root is not going to be the square root of the expected value. That's the difficulty in statistics or in probability. So here is the problem. So these are the greedy, these are the optimum solutions for the mean and variance. So this is in fact the uniformly minimum variance unbiased estimator of both of them. This is also an efficient estimator. This is not efficient in the sense the Cramér-Rao bound for this, the variance for this exceeds the Cramér-Rao bound. But here the variance is equal to the Cramér-Rao bound. So we are going to stay away from variance and we come to this. So this is, I thought this is interesting because this is generally not discussed. So we want an unbiased estimator. So how to find an unbiased estimator for the standard deviation. So let me start with some observations. Remember, so if xi minus x bar is the same thing. This is of course a Gaussian. Let me call this to be yi. I am going to call this as, so remember, xi's are, so the mean is this. Of course, this is xi minus x bar is Gaussian, but an interesting identity is that if you take this sum I equal to 1 through n here, I equal to 1 through n xi minus x bar, and this can be rewritten in this form. I mean, this takes some doing. Again, this is, I think this is explained here. So these are all messed up, right? Because x bar is a function of xi's, etc. But you can do a simple linear transformation and show that the sum involving n random variables. Remember, these are all, each of these random variables are correlated, because if I call this zi, they all depend on x bar, so they are correlated. But you can rewrite in terms of independent random variables where yi's are independent, but except it's only n minus 1. So you can say the degree of freedom here is n minus 1 because this takes away 1 degree. So consequently, if that being true, if I define z to be, if I look at this random variable, so this is the same as yi over sigma squared. So notice that yi's are IID normal with mean 0 and variance sigma. So yi over sigma is standard normal with the mean 0 and variance 1. So its square is chi squared with 1 degree of freedom. If you add this up, this is chi squared with n minus 1 degrees of freedom. So consequently, the density function of z is going to be z to the power the number of degrees divided by, this is again standard expression for 2 to the power 1 over 2. So this is this minus this, e raised to minus z by 2 for z non-negative. So of course this looks like this in general. So let's look at expected value of this quantity. Remember, the goal is this is not an easy problem. So I'm by one way or the other way, we are trying to find an unbiased estimator for z. So this is integral 0 to infinity square root of z fzc dz. So let me plug this in. So this is equal to so this is so notice that this z multiplies the minus 1 will go away, so this will become integral 0 to infinity z to the power, I mean minus half will go away, so this becomes z to the power n by 2 minus 1, right, and e raised to minus z by 2 dz. So I'm going to call z by 2 to be u, so that this becomes 2 to the power n by 2 minus 1. dc is, there is another 2, gamma n minus 1 by 2, 2 to the power n minus 1 by 2. Integral 0 to infinity so this is 2z, right? U is, I mean z is 2u, so I took the, instead of z I put 2u, so I took out the 2 term outside, so this is u to the power n by 2 minus 1 e raised to minus u du. So notice that this becomes this 2 and this goes away. So we end up with the square root of 2 over gamma of n minus 1 by 2. And this is gamma n by 2, right, by definition. So gamma n by 2 multiplied by alright, so we have, so whole point is expected value of square root of z is a constant and z is here. So from there we get expected value of square root of 1 over n minus 1 summation xi minus x bar the whole squared I equal to 1 through n. This quantity expected value is z multiplied by this. That's going to be sigma multiplied by, because there is a sigma squared here, so when I do the square root here, there is a sigma, and if I bring it to the other side, that is 2 gamma n by 2 over gamma n minus 1 by 2. So of course you see that now gamma n minus 1 by 2 to gamma n by 2 multiplied by square root of I 1 over n minus 1 summation sigma xi minus x bar the whole squared I equal to 1 through n is sigma. Remember, this is gamma expression. There's no, okay, so in other words, I just take the square root of this expression. So this is true. So if you want, so we found one unbiased estimator. We could say this one Z1 equal to gamma n minus 1 by 2 over 2 gamma n by 2 summation square root of summation xi minus x bar the whole squared I equal to 1 through n is unbiased for sigma. So this is one expression. Now we can try to find out its variance. So variance of Z1, for example. Remember, so we have expected value of Z1 is sigma, and variance of sigma 1 is expected value of Z1 squared minus sigma squared, because that's its mean. So let me substitute for sigma squared, Z1 squared. So that's going to be this was a square root here, right? And consequently, this is a square root. So this is a square root. So when I square it, you get half gamma n minus 1 by 2 over gamma n by 2 the whole squared. Expected value of sigma xi minus x bar the whole squared I equal to 1 through n or minus sigma squared. But notice that this quantity is same as sigma yi squared I equal to 1 through n minus 1, and so this is, each of them is yi's are Gaussian with the variance sigma squared, n minus 1 of them. So its expected value is n minus 1 sigma squared. So we can substitute it now. So the variance will turn out to be n minus 1 by 2 multiplied by gamma of n minus 1 by 2 divided by gamma of n by 2 the whole squared minus 1 multiplied by sigma squared. This minus 1 from here. So this is one estimator. How do we know whether this is the best estimator? We do not. Of course, we can compute the Kramerov bound and check it, etc. But in any case, since we found this by sort of ad hoc manner, it's easy to figure out that this is probably not an efficient estimator. So this is, at least we have, so let me summarize it. This estimator, we have an unbiased estimator for the standard deviation. A variance is a different story, but for the standard deviation, you need all these constants. So the hunch was more or less, if you take the square root of the variance, it's not going to be unbiased, but fortunately, it's only scaled by a constant. So bottom line is you can rescale it and make it unbiased, and this is the variance. So let me try a second method. So this is another idea. So all the xi's are zero mean variance sigma squared. So let me look at the expected, this is a standard problem, expected value of the absolute value of the first moment. So this is going to be integral minus infinity to plus infinity x fx x dx. And this is of course 2 times 1 over square root of 2 pi sigma squared. This being an even function, it's 2 times 0 to infinity x e raised to minus x squared over 2 sigma squared dx. And of course, if I define x squared over 2 sigma squared to be y, you have y dy equal to, you have x dx equal to sigma squared dy, right? 2x dx, 2 cancels. So we have x dx here. So this is square root of 2 over pi 1 over sigma. Okay, and we also have sigma squared, so integral 0 to infinity e raised to minus y. Then you have sigma squared dy. So 1 sigma cancels, and this integral is 1. So this is square root of 2 over pi sigma. So we can clearly get another idea for an unbiased estimator. So if you consider xi minus x bar, remember x bar is, xi has mean mu, x bar has mean mu, and so the difference is Gaussian with the zero mean. So we definitely know that this is Gaussian with the some variance sigma squared. We can find the sigma squared in a minute. In fact, so we can see that we can use the absolute value of this to get another, because from here, look, you have expected value of square root of pi over 2, absolute value of xi is sigma. So we can construct another unbiased estimator for the standard deviation using this idea. So let me define z, or z to be sigma xi minus x bar absolute value. So remember, xi minus x bar is normal, so its absolute value, expected value is proportional to its variance. So this is something we want to look at. So to see what this is, let me look at the, let me try to find out the variance of this, this quantity. Variance of this expression, that is sigma naught squared. So sigma naught squared is, remember this random variable is zero mean, so it's simply the square of that random variable, xi minus x bar squared. So that's going to be expected value of xi squared minus 2 xi x bar plus x bar squared expected value. So xi squared is mu squared plus sigma squared, and x bar squared is mu squared plus sigma squared over n. And this is 1 over n, this is 1 over n sigma xj. So you can see xi's are uncorrelated with all of them except xi. So it's 1 over n xi squared. So this is minus 2 over n. xi squared. So that's going to be mu squared O plus sigma squared. And when I is not equal to j, so that's going to be simply xi xj, but expected value of xi is mu I. So you have minus 2 mu squared over n, and there are such n minus 1 terms. So if you pull all this, this goes away, right? And all the mu squared goes away, and we get n minus 1 because from here, right, you have sigma squared. This is sigma squared over n. So this is sigma, so n minus 1 over n sigma squared. So that turns out to be the variance. So consequently, if you define z to be this random variable, look at the expected value of z. So expected value of z is going to be from here. Each of this random variable has mean of this form. So it's going to be n times 2 over pi square root sigma naught. But sigma naught, we have an expression here. So that's n cancels. So this is 2 over pi n minus 1 sigma squared. Sigma. So this is n multiplied by square root of 2 over pi sigma naught. The sigma naught is going to be square root of n minus 1 over n sigma. So some cancellation, and you get 2n minus 1 over pi multiplied by sigma. So again, we are ready to figure out another unbiased estimator. Consequently, z2, which is square root of pi over 2n into n minus 1 multiplied by z, which is summation xi minus x bar, absolute value of xi minus x bar I equal to 1 through n, is another unbiased estimator for sigma. So we have two unbiased estimators. One is Z1 here, other one is this. We already found the variance of the first unbiased estimator. So the next problem is to find the variance of this unbiased estimator. We had the second unbiased estimator as Z2. This is an unbiased estimate. We just showed that it's an unbiased estimator for sigma, the standard deviation. So what we have shown is expected value of Z2 is sigma, where Z2 is some constant multiplied by the absolute value of xi minus x bar. Let me call this quantity to be absolute value of Zi, just for notation's sake. So what we have shown is expected value of Z2 is sigma. In other words, this is an unbiased estimator for sigma, the standard deviation, based on the observations. Look at here, it all only involves the observations. Now the final job is to find out its variance. So variance is the square of the expected value of the square of the random variable minus sigma squared. So bottom line is how to find out. So this is going to be a constant which is pi over 2n into n minus 1 expected value of zi squared so this of course is pi over 2n n minus 1. This is I equal to 1 through n. So this is two terms, expected value of z. We also have shown that zi's are normal random variables with the variance sigma squared, zero mean. So if you substitute this, so this is going to be n minus 1. This is n of them. So the n cancels, you get n minus 1 sigma squared. And so the difficult part is, or the interesting part is here, I not equal to j, I equal to 1 through n, j equal to 1 through n, expected value of, absolute value of zi is zj. So this itself is a interesting problem by itself. And so I will at least sketch the how to do this portion, and then we substitute it here. So finally the variance is going to be this value minus sigma squared. So let's look at expected value. Let's look at the two Gaussian random variables which are correlated and have a correlation equal to some correlation coefficient equal to rho. So you have two random variables, two Gaussian random variables with equal variance and correlation coefficient rho. So what we want is expected value of x, this quantity. So this is by definition now minus infinity plus infinity minus infinity plus infinity x, y, 2 pi sigma squared 1 minus rho squared e raised to minus that exponent. So let me substitute x equal to r cos theta and y equal to r sin theta. This to change of variables. So dx dy will be, of course, r dr d theta. So this integral now becomes theta goes from 0 to 2 pi and r goes from 0 to infinity. So you have an r here, and r here. So you get r cubed sine theta cos theta, right, from here. And you have 2 pi sigma squared 1 minus rho squared e raised to minus r squared into 1 minus. So this is r squared sine squared plus r squared cos squared plus sine squared is r squared. This is rho cos theta sine theta 2. So that is sine 2 theta over 1 minus rho squared sigma squared dr d theta. We already took care of the r here. So now you simply substitute this whole thing equal to u. So that this integral now becomes integral 0 to 2 pi 0 to, so this whole quantity is u. So du is going to be 2r 1 minus sine theta. I guess there is a rho here. 1 minus rho sine 2 theta dr r dr divided by 2 into 1 minus rho squared sigma squared equal to du. So this integral becomes so r dr, so I'm going to write this as d squared r dr. So r dr becomes part of du. So you have 1 minus rho squared multiplied by sigma squared over 1 minus rho sine 2 theta. Then you have a sine 2 theta here divided by 2 pi sigma squared 1 minus rho squared. Then you have r squared. R squared is going to be from here. R squared is going to be u multiplied by 1 minus rho squared sigma squared over. So this is like this r dr d theta. 1 minus rho sine 2 theta. So some cancellation now. Sigma squared cancels with 1 sigma squared here. 1 minus rho squared goes away. And the rest of these terms, so you had here sine theta cos theta. Together with this 2, it becomes sine 2 theta. Sine theta cos theta, then you bring in the 2 here, so it's absolute value of sine 2 theta. So the bottom line is, if everything is right, this expected value turns out to be sigma squared here I believe this was a half here, so this is so this half cancels with the half here, then half and 1 here, so you have 1 minus rho squared to the power 3 by 2 divided by 2 pi, that's the constant, integral 0 to 2 pi, absolute value of sine 2 theta divided by 1 minus rho sine theta, 1 minus rho sine 2 theta, but that appears twice, so squared d theta multiplied by integral 0 to infinity e raised to minus u du. So this is 1, that's easy, that u part. Now this needs to be simplified. It takes a few steps. I'm just going to write down the expression for that. So that's let me simplify. First of all, notice that so because of 2 theta here, this integral is the same as going 2 times integral from 0 to pi. So I'm going to bring in a 2 here, 2 cancels. So you have sigma squared multiplied by 1 minus rho squared to the power 3 by 2 over pi. Then this integral is from 0 to pi, which I'm going to write it as 0 to pi by 2. But in 0 to pi by 2 sine 2 theta is positive. So I can write it like this. Plus pi by 2 to pi all right, so in this region, this is going to be negative because, and this will remain positive. So if you want, we can change this, this will become plus here, and this will be the same as this. So the limits are back to 0 to pi by 2, but this became plus. Now each integral needs to be, so you can combine those two integrals. Let me write one more step. So this is sigma squared 1 minus rho squared 3 by 2 over pi. So notice that, so when you combine this, this comes here, this comes there, and the denominator of course becomes 0 to pi by 2, 1 minus rho squared sine squared 2 theta, the whole squared, and in the numerator you get, when you square it, the middle term goes away, and you pick up a 2 here, then this becomes sine 2 theta multiplied by 1 plus rho squared sine squared 2 theta. So now I'm going to, now you can convert this into a variable quickly, because maybe let me show you that step, then I'll skip this. So sine squared theta we can write in terms of cos 2 theta. So sine squared theta is 1 minus cos squared 2 theta. And same thing here. This also we write in terms of cos squared 2 theta. Then if you substitute cos 2 theta equal to x, the derivative dx is going to be sine 2 theta d theta. So this you can convert it into a x expression. And I'm just going to write down the final answer. And when everything is simplified, this turns out to be 2 sigma squared over pi multiplied by square root of 1 minus rho squared. So I'll write it down. So this is 2 sigma squared over pi multiplied by square root of 1 minus rho squared plus rho sine inverse rho. So this itself is an interesting result. I'm going to take this result and substitute there, and that should, so this is the expected value of absolute value of x multiplied by absolute value of y, where x and y are normal with the zero mean and variance sigma squared. This is the problem we started with, and some correlation coefficient rho. So generally, again, you don't see this often. So you just need to substitute this. As I said, right, sine squared theta is 1 minus cos squared 2 theta, here as well as here. And then you make a substitution cos 2 theta equal to x. Then dx will be sine 2 theta d theta, and this gets converted into an integral from in x, and you can easily solve because it only involves up to quadratic terms and a square term. Right? So only thing we need is we just need this result here. So remember, zi's are, there's a little more stuff to do here, xi minus x bar, and we have found this to be normal with variance sigma squared, sigma naught squared, which is n minus 1 over n sigma squared. So no, but they are all correlated. So we need the correlation coefficient Zi, Cj. So this I'm just going to write it down. Again, it takes some doing. So this will turn out to be sigma squared over n. Consequently, Zi, Cj, the correlation coefficient between Zi and Cj is minus 1 over n sigma squared and n minus 1 over n sigma squared. So this will turn out to be minus 1 over n minus 1. So we need that quantity plugged in here. So this quantity is going to be 2 sigma squared over so we have 2 sigma naught squared over pi square root of 1 minus rho squared. The rho is here, so 1 minus 1 over n minus 1 squared minus rho. So rho is minus this quantity, so that's minus 1 over n minus 1 sine inverse of minus 1 over n minus 1. So this minus becomes plus. And sigma naught itself is, so we can simplify this also. This is 2 sigma naught is n minus 1 over n sigma squared. So if you substitute this expression here, we would get the, everything is solved now, because this is the, so this is going to be n into n minus 1 by 2 such terms, n squared minus n terms, so n multiplied by n minus 1 terms. So notice that this n cancels, this n minus 1 cancels with here and also cancels here. And sigma squared is common, so if I write it down, this simplifies to sigma squared over n, and the first term is pi by 2. And this term, of course, we can write it as square root of n minus 2 over n. And so let me write down the result. So if I substitute all this here, I'm going to get plus square root of n into n minus 2 minus n plus sine inverse of 1 over n minus 1. So that's the so actually this happens to be, and minus sigma squared, so this happens to be the variance of Z2. That's what we have been looking for. So this problem is interesting because generally you don't find the unbiased estimator for standard deviation. So we found the 2 unbiased estimators, and more importantly, what was interesting is to find out also their variances. So in this process, we did another classic problem, which is if x and y are jointly Gaussian zero mean random variables with equal variance and correlation rho not equal to 0, what is the expected value of absolute value of x multiplied by absolute value of y? And that answer is there. And this is the variance. Again, this is by no means, it's not clear. Certainly, none of these are the minimum most variance estimators. But if you plot these two variance against n, you can see they are at least a relative efficiency.